So next up we have Maciej and Mateusz, and they'll be talking about telemetry enhanced green computing or coding. Yeah.
Okay, welcome everybody. My name is Maciej Lawniczak, and together with Mateusz Duchalski, we'll tell you today about green coding and how sustainability telemetry can enhance this trend. Okay, so in today's presentation, we'll tell you what green coding is, what are the green coding best practices, and how telemetry, what type of telemetry can be used to enhance that trend. Then we'll show you some of our green coding experiments, and later on, we'll try to predict the future of green coding, and we'll wrap up with a call to action. Okay, so green coding is a part of a broader term, which is green computing. And green computing focuses on environmental sustainability of IT compute in general. So here in this trend, for example, we have like sustainability, analyzing sustainability aspect of hardware product lifecycle. We have energy efficiency of all the components taking part of IT compute. So software and deployment part of this trend is where the green coding fits in. So green coding is a set of best practices and techniques to improve energy efficiency of your application. So in simple terms, how to code your app to make it more green. And we can extract few groups here. So we have like virtualization, resource allocation, data compression, software power management, and the last one, the most important from the perspective of this presentation, is algorithmic efficiency. Okay, on the slide I wanted to show you some of the green coding best practice divided into different categories. So first we have infrastructure, and it basically relates to the transportation and storage of the data. And as an example here we can take caching. So reports show that we can save up to 70% of energy with a single level caching in video streaming services. Next one is deployment. So here we have like cloud deployments, virtualization, so everything that helps to better utilize the hardware. And the last one, the most important for this presentation, is processing. So here we have, for example, programming language choice. So there are many great papers out there in the internet that are talking about energy efficiency of specific programming language for specific use cases. We have computing hardware choice. So in the times where processor is not the only thing that is doing the computations, we have GPUs, we have other types of accelerators. Choosing the best hardware for a computation is very important. Next, we have computation accuracy reduction, power management. These are also great tools for green developer. And the two last things which we will focus on in our experiments are green algorithms and green libraries. Okay, so let me move on.
Thanks, Maciej. So in order to effectively implement any of these green coding practices, we need to be able to measure the outcomes, right? And this is where the telemetry comes in. Now, in general, the data center telemetry requirements are very diverse, right? The usages may span many different layers from an individual system and its components all the way up to the entire data center. And this is also certainly true for the sustainability telemetry. Then there's the matter of what we actually consider relevant telemetry for green coding, right? And obviously, the main outcome and the main thing we'll want to monitor is the energy usage, but the set of metrics that you might want to monitor may be broader. For example, you might want to look at resource utilization to see if you don't have idle systems wasting energy. You might look at how effective power management features are, like monitoring low power state residencies in CPUs and so forth. Finally, some environmental factors like thermals might also be relevant to you, like monitoring how well your water-cooled solution is performing, etc. And all of that can help in different aspects, both the software development process and data center operations. Today, we're really only going to focus on the CPU telemetry subset. So zooming in on that a bit, let's look at some of the examples of those usages and how a modern CPU can deliver telemetry to support them. So here we've listed some of them. I already spoke of some here, and this is also certainly not a comprehensive list, just examples. But generally, all of that requires some telemetry to support, right? And here we've used an Intel Xeon CPU as an example of a product that can deliver it. Specifically, we looked at 3 sets of telemetry. So first one being RAPL MSRs, which on an Intel Xeon provide the ability to measure package and DRAM energy. Then we looked at platform monitoring technology, which on more recent Xeon CPUs can provide, for example, voltage, frequency, temperature histograms, which might be useful in this kind of monitoring usages, which we'll actually mention in a second. And last but not least, perfmon is very well known and provides an exhaustive list of events enabling you to understand the execution of a CPU workload at a very low level. And in the same way as this can be incredibly useful for like performance tuning, it can also be used to understand differences in energy efficiency between applications. Today, we're really going to focus on this software development usage. So we're going to be using those RAPL MSRs to extract energy consumption between different workloads and make some conclusion based on that. We're also going to briefly touch on the PMT. So moving on to our experiments, how we were able to use CPU telemetry to evaluate the effectiveness of some examples of green coding best practices. So we looked at a few. We looked at following best practices for a given programming language based on a Python example. Then we looked at a simple example of selecting the most energy efficient algorithms and libraries between Python, C, and C++. And finally, we looked at how we could potentially use compiler optimization option tuning to achieve better energy efficiency. And for all of our testing, we built a simple test setup illustrated on the right-hand side. So for each of those examples, we would essentially just run a set of executables, like tens or hundreds of times each, depending on the specific one, collect PMT and energy telemetry in the process, and then work on the aggregated data. We used an Intel Xeon-based server with the Sapphire Rapids CPU as a test platform. And now let me hand over to Maciej for the first example.
Okay, thank you, Mateusz. So I'm a great Python fan, so I'm really happy that this is our first experiment. So one of the first things that you learn in this programming language is how to properly create lists using list comprehensions. So we decided to compare the energy difference between creating a list of 100 million elements between list comprehensions and for loop list creation. So let me show you the results. So on this graph, you can see the comparison between energy, average power, and execution time. And as you can see, winner by a large margin is list comprehensions version. So for loop version is 66% slower and 68% less energy efficient than the list comprehensions version. And the difference in the energy saved here is like enough to power your standard LED bulb for like 34 seconds. So to sum up, list comprehensions is better than the for loop list creation, but to generalize, we encourage you to use the language-specific programming recommendations in your code. Okay, and remember when I told you about algorithmic efficiency? So here in this second example, we'll compare 11 different sorting algorithms provided by PySort library. And the task will be to create, to sort a list of 1,000, 10,000, and 100,000 samples, and each of the samples from the range of 0 to 1 million. So here are the results for 1,000 samples. So in general, we see that there is a strong correlation between execution time and energy consumption. But as you can see, we have a single exception here, which is bubble sorting algorithm. So we decided to dive a little bit deeper into that example. And so for that, we use Intel platform monitoring technology to check what is happening with the core that is running this workload. And as you can see, bubble sorting algorithm is not fully utilizing the core that it is running on. So the average frequency, average temperature of this algorithm is lower, much lower than average for all the rest of the algorithms. So we didn't dive deeper to check why is it happening, but yeah, these are the results that we were able to check. Okay, so now the results for 10,000 samples and 100,000 samples. So this time we do not see an exception for the energy to time correlation. But one thing it's worth to mention is that with the number of samples, the difference between the worst and the best algorithm is becoming more significant. So for 10,000 samples, we have like almost 90 times more energy used. And for 100,000 samples, it's almost 6,500. So it's enough to charge your cell phone. So to sum up, a green developer understands the data that he's working on, and he chooses the best algorithms for his specific use cases. So now let's move to the next experiment.
Right, so now let's look at selecting the most energy efficient library for the same task, right? And here we've arbitrarily picked parsing as an example and looked at specifically JSON and XML parsers for Python and C++ respectively. And between the two, we've tested about a dozen popular representatives. The test scenario was very simple, just to parse and serialize the file again for JSON and parse the file to an internal representation for XML with slightly different implementation depending on the type of the parser. In both cases, we've used like a few hundred megabyte large file as an input. Let's take a look at what we came up with. So on the left-hand side here, you can see the results for Python JSON libraries, right? The energy usage and execution time, as shown before. And the main takeaway here really is how those relatively similarly featured libraries, the differences between energy usage between the most and least energy efficient one is quite substantial, right? This is like 3x here or something like that, and actually enough energy for this single file to like watch television for 6 seconds. In terms of this energy time correlation that we keep coming back to, it's holding strong here, so not much to report. For XML, it's much of the same story, but one thing of note is how the magnitude of the differences between this least and most energy efficient library is, or variant is even more substantial, right? This is like 50x here or something like that. Now, this is not apples to apples in all cases. Now, for example, the libraries on the left-hand side are more performance-focused. The ones on the right-hand side are more feature-rich, focused on compliance, etc., as you'd expect. But in general, we think that together with the JSON example, this is a good illustration how it is useful to consider energy usage when picking out components of your software stack, like libraries. And actually, this difference here, I forgot to mention, between the most and least energy efficient library is enough energy to power like a 3.5-inch hard drive for 7 minutes, so it's not that trivial. So now, moving on to the last example that we have, how we were able to, sticking with this XML one, but instead of looking at the choice of the library, on how we can potentially tune compiler optimization options for lowest energy usage. Now, we've looked at GCC, CLang, and the Intel compiler here, and ran through a bunch of different configurations. So let's take a look at what we were able to see. So here you have the comparison of the effects of those optimization options for one of the libraries. This is RapidXML. It's just where we saw that the differences were the most pronounced. And on the y-axis here on this chart on the left-hand side, you have deviation from per library mean. So how to read this is basically the average energy usage, average execution time across all of those compiler optimization options, all of those compilers for RapidXML would end up at 0 on this chart. And then, for example, on the right-hand side, this worst performer, which in this case turned out to be this GCC with size optimization, achieved roughly 15% higher energy usage and roughly also the same 15% higher execution time. This is the green and orange bar, respectively. So what are the takeaways here? So first of all, notice how minor things, so enabling CPU native optimizations, right, those Sapphire Rapids options here, this seems to be pretty effective. Note that for each individual compiler, this was either the most energy efficient one or at least within margin of error. And the second thing of note is that we can start to see some deviations from this time energy correlation that we keep coming back to here, right? Probably most notably for this right-hand side example of the GCC with size optimization. Now, actually, we looked at this specific case in a bit more detail, and it turned out to be quite interesting in that it actually performed quite well across other libraries. Now, note the scale, though. This is very small magnitude of changes, but still well beyond the margin of error. And what is more notable here is that this also consistently breaks this energy time correlation, right, which is very apparent on this chart here. Now, we didn't really dive deeper into why that is, but I think it serves as a good illustration of how it's valuable to look at energy usage specifically when tuning compiler optimization options and other tunables similarly to the libraries. All right, so wrapping up the examples we went through, what have we learned from all of this? So a few things. First of all, between most of them, we've seen that the correlation between execution time and energy usage is, as you'd expect, pretty strong. So if you don't know where to start, just remembering that performance matters for energy consumption and that it might be valuable to prioritize even if your application doesn't have strict performance requirements otherwise, it's probably a good starting point. But even in those quite textbook, trivial single core cases that we illustrated, faster didn't always mean most energy efficient. We saw indications of that just now with the compiler tuning. We saw some indications of that with the algorithm efficiency. So there really is a case for having this kind of dedicated sustainability telemetry to guide green software development. And the other thing that is apparent based on even those simple examples is how small design implementation decision can significantly affect energy use, right? So taking this into account includes following the best practices for a given programming language, but also just use of profiling to identify the most efficient algorithms, libraries, compiler options, and really any other degree of freedom you might have in your software stack. So now, wrapping up, how do we see the future of green coding developing? We think potentially energy-targeted optimization might be integrated into compilers and interpreters. Then when you're focusing your process or taking the energy usage into account in your software development process, you want to track it. You want to find regressions, right? And this is where we potentially see this being integrated into like CI/CD flows. Then to aid this kind of how to select the most efficient X kind of exercises, we think there's potentially value in developing kind of like sustainability rankings, public sustainability rankings of applications, libraries, and other tools. And finally, for more of its implementation aspect, we think that potentially static analysis might be a good tool for guiding adherence, and potentially even see tools like that being integrated into development environments. So now let me hand over to Maciej to wrap up.
Okay, thanks, Mateusz. Okay, so a few actionable items that we would like you to take from this presentation. So first one is to focus your development process on sustainability. So how can you achieve that? We propose three things. So first one, use sustainability telemetry to guide your implementation and design decisions. So for example, if you have two versions of code, measure their energy efficiency and select the better one. Next one is add sustainability aspect to your code review process. So you probably already have like security, maybe you have performance code reviews, add also sustainability aspect to that part of the development process. And the last thing here, add sustainability telemetry to your CI/CD pipeline. So if you have like some basic tests that you're running on each build, then add telemetry, sustainability telemetry to that, and include it in this pipeline. So then you will be easily able to spot the regressions, energy-related regressions, and fix them. Okay, next thing, encourage and support green coding initiatives. So we know that there is always a time pressure, to getting ahead or on time or ahead of with your product to the market. But spending some time on energy efficiency of your code could really save a lot of money for your organization. So it's a good idea. Next thing, expose sustainability telemetry in new products. So if you're a hardware, firmware developer, add sustainability telemetry to that. So the applications that will be running on your hardware will be able to tune themselves based on these metrics. And last two things, support sustainability researchers related with the tech industry and share your green coding, best practices, processes, and tools with the community so everybody could leverage that. And guys, remember, we are all fighting for a greener future for us and for the future generations. So thank you.
Thank you, Matthias and Maciej. Do we have any questions for them?
Guys, that was super cool, so thank you. That was really neat.
Thank you.
So the time-energy link looked good, and then at the end you kind of said, well, maybe not, we should focus on energy. I loved your conclusions, and I think you're right. Every coder on the planet wants a better planet, but is under ridiculous time pressures to meet goals. So I love the best practices, but can you see in your work the idea of creating some kind of a average metric? I run data centers, so PUE, REF, WE.
Yeah.
Can you see anything like that coming out of what you're looking at?
Yeah, so I think one of the ideas that we have is to create some kind of, maybe not consortium, but this is too much, but some kind of tool that will measure the energy efficiency. So basically energy use for some, standardized task for applications, for libraries, similarly featured. And that could be, let's say, published on the internet. So for example, if I'm a developer and I want to, let's say, parse the JSON and I want to do it energy efficiently, I can go to that and check, okay, so this library has like, 8++ rating, so I would select that one.
Yeah, thank you. I think we are at time, so appreciate it.
Thank you.